you stupid machine. Hello, those of you watching online. I'm David. I'm the coordinator of the Maths Learning Centre. It's Semester 1 2019. This is a revision seminar for Differential Equations II. And given a rather comprehensive list of things to talk about, mainly stuff at the end of the course by the look of it, if I've got this right, things about PDEs and the Frobenius Method and that sort of thing. So, my disclaimer, star, batteries not included, is that I am not a person who teaches this course. I have nothing to do with the assessment or the lectures or the exam. So I can't tell you, and I'm also not telepathic, so I can't tell you what your lecturer is thinking. So if you have a question that goes, would the lecturer put this in the exam? I don't know. We can make some reasonable guesses based on how much time you have in the exam, but I don't know. Does the lecturer expect me to remember this? No idea. But if your lecturer has given you the opportunity to take some notes with you, then I expect that there will be things that he expects you to put on there. Not necessarily remember, but have put on your memory support device. So I also can tell you that most lecturers, if they give you the ability to bring in a cheat sheet, will not ask you for the definitions of things as in questions in their exam, because that would just be copied off your sheet. They'll just launch straight into questions about doing things. That's usually how lecturers behave if you have a cheat sheet. So just letting you know that. I'm just going to take all definitions and theorems as read and just start using them. But I could be wrong. The genre of maths exam, which generally goes question A, definition, question B, quick thing that uses the definition, question C, hard thing, is very strong and difficult to break out of if you're used to writing exams that way. So, yeah. So in the end, I don't really know anything about what your lecturer is going to put in your exam. But I can at least help you make, together we can make sense of some of these things. So, to reward whoever wrote the first thing on the board, I will talk about Frobenius' method first. Okay. Page 62, let's go. Okay, so this is the part of the official lecture notes that talks about Frobenius' method, and it says that it's section 5.3 in the 2011 version of Kreisig. It's got some definitions about singular points. It starts off with Bessel's ODE, which apparently describes the radial structure of the vibrations of a drum, waves in a paddling pool, and many other problems in circular cylindrical geometries. Or maybe that's what this is about. Could be wrong. Okay, so we've got things about singular points. Mostly okay. Does Frobenius happen earlier than this?
It's mostly referred to the textbook.
Okay, sure. Oh wow, launches straight into the Bessel functions straight up. Okay, I shall go to the textbook. Well, it must be nearby to this. I don't care. I want something that I don't have to keep switching between the screen and the document camera. Frobenius Method 215. Okay, so just like the power series method. Okay. Or am I allowed to just make one up and run with it and see what happens? I don't have to do the Bessel's one, and I feel like that's done a lot, and so I'm just going to pick a different one. So, as far as I can tell from what the notes were saying there, Frobenius' method is a power series sort of way of dealing with for essentially second order DEs, but for linear DEs by the look of it. And actually it's pretty much for second order ones by the look of it too. Okay, that's good to know. And according to the book, it only works for things like this. Where BX and CX are analytic. At x equals 0. So presumably it will also work for things that have x minus a and x minus a squared as long as they're analytic at x equals a. So, but apparently we tend to focus mainly on things where that x is, where it's 0. Okay, and that's called so a point that's not a regular point is called singular, which would mean one where these two are not both analytic. Singular point. And it doesn't talk about it here, but over in the notes it talked about there being a regular kind of singular point. So it looks like, according to the notes, so a singular point, where's 6.3? Okay, so a singular point is a place where if we put it in standard form, which means dividing by the h, we end up with everything being analytic still. And a regular singular point is one where if I multiply this one by x and this one by x squared, so this one by x and this one by x squared, I get an analytic function after all. And what the textbook is saying is exactly that. The thing that is next to y, when I multiply it by x, I end up with an analytic function, which is what bx is. And the thing that is next to, sorry, that's y dash. The thing that is next to y, if I multiply it by x squared, I get an analytic function. Okay, so I just want to match that up with what the lecture notes said. This was the textbook. And this is the notes. Does it have to be? Oh, we do the homogeneous one first anyway, I guess. X times px and x squared times qx are analytic. Okay. So they're the same thing, but it's good to be able to compare them. I'm just trying to understand what's going on here. So I presume that if they've talked about it in the notes in a certain way, this is the lecturer's preferred method. And that's what the textbook says. But they mean the same thing. Okay, cool. So I reckon I can set up one now and just do it by example. He's found it. Sure, let's do that. I don't know if this is going to be at all helpful. I'm going to put a number here as well, just to mix it up. Okay. So that's a second order linear differential equation. In standard form, I get this. I get that. And this does have the property that if I multiply this one by x. So it does have x as a singular point. Neither of these exist when x is 0. They're not analytic there. So x equals 0 is a singular point. And this one, if I multiply it by x, I get a polynomial, which is a perfectly good analytic function. And this one, if I multiply it by x squared, I also get a polynomial, which is 3x. So it's a perfectly good analytic function. So this fits the format. So we have x equals 0 is a regular singular point. I should probably put a reason there, since x minus 1 over x and 3 over x are not at x equals 0, but x times x minus 1 over x, which is x take 1, and x squared times 3 over x, which is 3x, are analytic at x equals 0. That's what it means to be a regular singular point. And as far as I can tell, we can only use Frobenius' method if that happens. So if we have irregular singular points, where if we multiply one by x and the other one by x squared, this won't work, apparently. All right. Okay. So, as far as I recall, we're going to assume that it's a power series. Does your lecture use n or m? N? Okay. It doesn't matter, but it's nice to match. Okay. And except not this, because this power series is analytic when x is 0, and that's our function y probably doesn't do that because of these weird-ass singular point of x equals 0. So I might have to move it back or forward by a little bit in terms of the powers. So it'll be like that. Yeah. Okay. So that's what makes it different from an ordinary power series thing. An ordinary power series has this, but that will only work if all your functions involved are analytic. And so because ours has a singular point, we're going to have to adjust it a bit. That's the difference. And the reason I mention that is that one of the important ways of being able to process any information and or remember things is to know how they're similar and how they're different. So, yeah. Okay. So then, as is classic with most of these methods of solving differential equations, they all tend to have this format where you go, this is what I think the y should be like, and then let's sub it in and see what happens. They all run by that method. So that's what we're going to do. So the AN will still be there, the power will come down, and the power will go down. All right. And then the second derivative will be this. So that's a number, it'll still be there. We'll multiply by the current power, and the power will go down by 1. If that R wasn't there, I would probably start this one at 1 and this one at 2. Sorry? If the R wasn't there. And the reason I don't do it when the R... So the reason I do shift this to start a different point where the R isn't there is because if there was no R...
Are you assuming for the second one that R is greater than 2? Greater than 2?
No.
Because otherwise, we're going from 0 and R is like 1, we end up with x to the minus 1.
Yep. That's okay. The whole point of this is that your function might actually have a discontinuity when x is 0, so it might actually have an x to the power of minus 1 in it. Yeah. So if it was just this, with no r, then when n is 0, the first term is 0 anyway, because you have an n 0, and it's not like there really is an x to the minus 1 in it. And so you would say, well, it really starts at 1. But since we don't know what r is, r might be a half, in which case, when n equals 0, you'll get x to the power of minus a half, and that's a perfectly reasonable function that we're allowed to use. So we have to keep it there just in case. We can't be sure until we know what r is whether the first term is 0 or not, and so we have to leave it there. To be fair, when you do it with the other one, you can probably leave it there anyway, like not actually adjust it, and it'll still be fine, but anyway. Okay, but with the other one, we don't want to give the impression that when you differentiate 1, you get 1 over x, which is what happens in the old one. Whereas in this one, if you differentiate x to the half, you might get x to the minus a half, and that's okay. Okay, so then what we're going to do is we're going to substitute this back into the actual equation that we had. And so I will try and keep the equation in view. Okay, so we need x lots of y double dashed, and we need x minus 1 lots of y dashed, and we need 3 lots of y. So I may waste a bit of paper and a bit of time, but I need to do this for myself to be able to get it right, so bear with me for a minute. So x times y double dashed will be this times x, which will make the power go up by 1. So we multiply this by x, multiply that by x, and we get an extra, power goes up by 1. Okay. X times y dashed will be this. So we'll take y dashed and I'll multiply it by x, and that will make the power go up by 1. And minus 1 times y dashed so that's these two pieces here. I just did them separately because it was easier for me to deal with it. Each term of the polynomial here I've just dealt with separately. And 3 times y is this. Okay, so all of these together, when I add them together, it's supposed to come out to 0. These 4 pieces here is this entire equation. If I add these all together, it's supposed to come out to the 0 function, according to this here. Okay, and at the moment it's going to be difficult to add them together. I can add these two because they have the same powers, whereas these ones, the powers are off by 1. And so I need to adjust enough of these so that the powers line up, and then I'm going to be able to add the coefficients directly as they are. If I had given myself, I really should have, I always forget to do it, I should have given myself a space after each of these to write down the adjusted version, but I didn't. I'm sorry. So.
Is s plus r minus 1 or like
This one? What am I looking at? No. Can you point closer? Because I don't know which line you're talking about. Minus 1? Oh, yeah. Yep, totally. Thank you. There's a lot of stuff on this page. That totally should be an n. Thank you. I didn't even need to tell you guys about how I'm okay to be interrupted. That's still the first years. Okay, so then I'm going to need to adjust them. So we get, which ones am I going to adjust? It seems easier for me to move these ones over to match with the n plus r, because then there'll be less minuses floating around, or at least, well, less minuses in the powers anyway. But there's nothing stopping me adjusting these two if I prefer. It doesn't matter which ones I adjust as long as they're all the same. It might even be easier to adjust these two because there's less n's involved. So normally if I was in an exam I wouldn't actually rewrite all of these, but I need to do it for the purposes of keeping this. And actually I'm going to adjust these ones. Okay. So what I would like is for this to become an n plus r minus 1. So it matches this. And that means I've subtracted 1 from all the n's. And so it'll be n minus 1 and n plus r minus 1. I've subtracted 1 from all the n's. So since I've subtracted 1 from all the n's, I have to add 1 here to account for that difference. So I subtracted 1 here in where all the positions where the n was, and I added 1 here. But of course, infinity plus 1 is still infinity. So that's okay. All right, so that's been moved over. Yes, it is. As I've mentioned in provision seminars before, wouldn't it be nice to have a team of people looking at what you're doing in your exam and finding mistakes for you? No. So this one doesn't need to be shifted because it's already in the right format. And then the last one does. So it has to go down 1, and therefore this has to go up 1. Okay. Right, well the sum of all of these is 0, according to the original equation. And that means that all of the coefficients of x to the whatever have to be 0, because the x to the whatevers are a basis and they're linearly independent and blah, blah, blah. We're going to equate coefficients. We're going to equate the coefficients here with the coefficients here. Okay. So what I'm going to do is I'm going to find the earliest n that is in any of these sums. The earliest n in any of these sums is n equals 0. Sometimes you end up with the earliest n being -1, sometimes you end up with the earliest n being 1, sometimes you end up with the earliest n being -1. It doesn't really matter. You find the earliest n that is mentioned anywhere in these sums, and that's the one you do first. And it is usually, and almost always true, that that earliest n doesn't appear in all of the sums. It only appears in some of them. So technically this is going to be the coefficient of x to the r minus 1, because the n is 0. Okay, so let's have a look. When n is 0, this one is a0, 0 plus r, 0 plus r minus 1. That's the coefficient of x to the n 0 plus r minus 1. This one doesn't have an n equals 0, so I skip that one. This one, a is minus a0, 0 plus r, and it doesn't have, and that would be that. And this one doesn't have an n equals 0, so that's it. So this coefficient is supposed to be 0. I did it to myself. No, that's all right. So I've just factorised these both have an a naught and they both have an r. So I factorise that out to leave an r minus 1 and a minus 2. Okay. Yay! And so the initial equation is this bit. Without the a naught. The reason we assume that a naught isn't 0 is because usually if a naught is 0, because we're going to get a recurrence relation later, if the first coefficient is 0, you tend to, because of the recurrence relation, make all the other coefficients 0. And we knew that already. Like the 0 function is certainly a solution to this. And so we don't need to worry about that one. So we technically assume that a naught wasn't 0 here. Okay. So the initial equation is that. And this tells me that if this process is going to work at all, r has to be either 0 or 2. Like that. Sometimes the initial equation will give you r equals like minus 1 and a half, or r equals, it'll be any usually, the way these are written, any rational number is possible, but technically any real number is possible as well. There will be weird-ass things happening when they differ by an integer like this. Yeah. So you'll notice that r equals 0 actually goes with this being an ordinary power series, because r to 0 is 1, and so this is actually an ordinary power series. And when r equals 2, it is still a power series, it just starts at x squared instead of at 1. So it would have been very nice if I had chosen one that didn't come out to that came out to something with like a half power. That would have been nice. But let's see what happens. So now that we know what r is, we have to pick one of the two values of r, probably both of them, but pick one of them and see if we are able to produce solutions to this. So, right. Which one do you want? In 0 would be nice. It's the simplest one. Pick 2. Yeah, because we know how to do power series. Let's choose r equals 2. Okay. So that's what we're going to do, but that's not going to come into it for a minute. So the thing is, we still haven't finished equating coefficients. We've equated the coefficient when n is 0 and gotten this thing that tells us what r is. And now we have to equate the coefficient when n is 1 and 2 and 3 and everything else. So I'll just look to see what the next n that is mentioned is. And the next n is 1. And 1 actually appears in all of these sums. And 2 appears in all of these sums, and 3 appears in all of these sums. So from this point forward, I can just do it in terms of n. Because the n appears because all the n's after 1 appear in all of these sums. Sometimes you have, 0 is in a couple of them, and then 1 is in 3 of them, and it's not until 2 that the n appears in all of them. So any n that doesn't appear in all of the sums, you have to do separately. But we are lucky because every other n greater than 1 is in all of these sums. So n is greater than or equal to 1, n equals 1, 2, etc. appears in all sums. Okay. So what have we got? So we have the coefficient of x to the n plus r minus 1, and I'll do it in terms of r in a minute, and then I'll sub the r in. So what have we got? We've got n plus r, n plus r, n plus r minus 1. And we have n minus 1, n plus r minus 1. And we have minus n plus r. And we have 3n minus 1. And that's all supposed to be 0. In fact, we can do all of this with the n plus r minus 1s in it and just sub in the r equals 2 at the end. I think that might be more productive, because then we can also sub in the r equals 0 at the end and do the other one if we wanted. So what have we got? So the goal here now, this equation relates an and an minus 1. It tells us how to get each one from the other. So what we like to try and do is get a formula that tells us how to find the later an's from the earlier ones. And so we need to get the latest n that appears in this on the left-hand side and everything else on the right-hand side. So n minus 1 is earlier than just n, so that's going to go over here. And we're going to aim to get an equals. So our n plus r, just factorise that bit. And I'll just factorise this bit. It just seemed reasonable to collect the an's and the an minus 1s together. Like that, so that plus 3 is there. And I've just simultaneously simplified that and moved it to the other side by putting a minus here. And so my an is a minus an minus 1, n plus r plus 2 over n plus r minus 2. Sweet. This is a recurrence relation. It tells me how to figure out each an from the earlier one. Okay, the whole thing is the recurrence relation, actually, all of it. And so if a is 2, if n is 2, if r is 2, an is minus an minus 1, n plus 4 over n plus 2 n, if r is 2. Cool. So what that means is that if A0 is whatever it is, I can figure out what all the other ones are. So A0 is A0, we don't know what that is. And A1 will be minus A0, 1 plus 4 over 1 plus 2 times 1. Just subbing in that n equals 1 into the formula, it should tell me what that is. So we got 5 A0, and A1 is minus A2 is minus A1, 2 plus 4, 2 plus 2 times 2, which is minus 6 over 8. A1, but we know what A1 is. Which is that. And so it should be possible to write everything in terms of A0 and so on. It's a classic thing for lecturers, at least over in Engineering Maths 2A, I don't know if they do it in Differential Equations 2, to just ask you in an exam to tell you the first few terms. Yep. Sorry? Is what not positive? Yes, it is, because this was a minus, wasn't it? Got it. Yes, because the A1 was a minus 5/3. Cool. and so on. I don't care to do any more of them, if that's okay. And so it looks like my y, which is a0 x to the r plus a1 x to the r plus 1 plus a2 x to the r plus 2, etc., will be a0 x squared plus minus 5/3 of a0 x cubed plus 5/4 of a0 x to the 4, and so on. Because the r is 2. Which is cool because you've got a multiple of a function. So presumably when x is 0, we'll get a different one. But I have a feeling that there's a theorem that says that if the initial roots differ by an integer, then the two solutions you get will be not linearly independent. They'll be linearly dependent. Because, I don't know, some sort of reason. So, there you go. Okay, so that's my understanding of how Frobenius' method works. I do have, it is over in Engineering Maths 2A, so when I do the website tomorrow morning, or at some point tomorrow, I will try and find, if I haven't put them on your webpage already, all the ones that I've done for them. You can find some extra examples if you're looking for them. Okay, any questions or what ifs or things like that that you want to talk about? Yep.
What was your reasoning behind choosing n plus r minus 1 instead of n plus r?
My reason, that's an excellent question to ask how I made my decisions. My reasoning was that it would require me to change less of the n's. Because shifting these two, there's only 1, 2, 3, 4, 5 n's here that need to move, whereas these ones require 1, 2, 3, 4, 5, 6, 7 n's to move, and so that's what I did. I decided to shift the ones that involved fewer n's. There was no good reason other than that, and you could have just as easily shifted the other way. But I just felt like my tendency to lose minus signs makes it easier for me to make a mistake if I have to affect more n's. And it did work out quite well, actually, because my recurrence relation ended up being an and an minus 1. If I'd shifted the other way, if I'd shifted these ones, I shifted these two down. If I'd shifted those ones up, I reckon it would have been an plus 1 and an, and it would have been a little harder to interpret, actually, so it worked out quite well. Yeah. So there you go. Maybe it is useful to shift everything to n plus r minus 1. Or not, I don't know. Maybe it's useful to shift everything to the lowest power in order to make the recurrence relation work nicely at the other end. Who knows? I don't have enough experience with this to be able to check, but I just knew that my own self, with my own ability to make mistakes in certain places, that's why I chose. But that's how it would have affected it. This would have been n and n plus 1 and n minus 1 here instead. Cool. So, let me just look at these. It should be possible for most functions to be able to turn this recurrence relation into a single formula for what an is. If you focus very carefully, because things are going to cancel with the later terms, and you should be able to go, well, each of them uses the two n's before it. Where's the one for n equals 2? Each of these, an uses n and n plus 2. So an plus 1 will use n plus 1 and n plus 3. this is n plus 5. So when we do, we know that each of them multiplies by the ones before, so some cancelling should happen later on at some point. Don't really know how this one's going to work. When they do the Bessel functions, everything works very neatly. And I just want to see if I can do this with the Bessel thing. I want to make sure I can make this happen. So how does the Bessel's function normally go? It's on the computer. Like this. X squared y double dash plus x y dash plus x squared minus nu squared y. Okay. Like that. And so I can see that if I divide by x squared, I'll get 1 over x, which doesn't exist when x is 0, so I have a singular point. And it's a regular singular point because when I multiply by x squared, everything becomes a proper polynomial. This process with the power series is only going to work if the functions that are in these positions are polynomials. Because that's, multiplying by polynomials shifts your powers over a bit. And so if it was like e to the x, we'd have to multiply e to the x, and so you'd have to have Taylor series and stuff getting really complicated. So it'll only really work if these are polynomials. So, well, let's try it. Okay. This bit's always the same. These derivatives will happen the same no matter what. And then I'm going to multiply everything by the various bits. So let's see, x squared, y double dashed, a n plus r minus 1, x to the n plus r. That's pretty cool. And x, y dashed, a n plus r, x to the n plus r, because that'll go up by 1. Ooh, they match. That's kind of cool. And then x squared y a n r plus 2, and then minus nu squared y Okay, so the only one, they all have n plus r except one of them, so that's the one I'm going to switch. Because there's, the other one there was 2 of each, and so it was hard to make the decision, but this one's easier for me because I'm just going to keep all these the same and just move this one over. So that one's going to be the same as, we want to shift these ones down by 2, and shift this one up by 2. So the ends here went down by 2, and these ends went up by 2. So now everything's in terms of n to the x plus r, and I know that the sum of these is 0, so all the coefficients have to be 0. So let's do it again. The earliest n is 0, and so that's the one that's going to produce the initial equation. And so we're going to get a 0, 0 plus r, 0 plus r minus 1 from this one. We're going to get a 0, 0 plus r from this one. And this one doesn't have n equals 0, so and that's all supposed to be equal to 0. I can divide by the a naught, and so I've got r minus 1 plus r minus nu squared is 0. Oh, how interesting. Oh, cool. That's so cool. Okay. I can't draw new without looking like a V. Okay. That is so cool. No wonder they like it. Okay. And so we have to pick one of those to get a solution. And so we might pick the positive one because the negative one will just have minus signs everywhere and that'll be annoying. Yep.
Plus or minus V, doesn't that mean it's always going to differ by an integer?
V might not be an integer.
Yeah, the difference between them will still be.
But if V was like a quarter, then the difference between plus a quarter and minus a quarter is a half. So in the textbook here they talk about what will happen if V is not an integer. So I guess the only non-integer for which differing by an integer would be a problem would be V equals exactly a half. Well, nu equals exactly a half, because half and minus a half differ by an integer. Actually, no, all the halves would do it. So you don't want nu to be something and a half, or a whole number. That would cause them to differ by an integer. Good. Okay, so if nu is anything that it's not an integer and it's not an integer and a half, then we can just do them separately and it'll give us two different solutions. Okay. Sometimes you actually get two solutions from just one of them anyway, because because sometimes your recurrence relation has n and n minus 2, so it only tells you every second term, and so you end up with A0 and A1, and you get two solutions. Well, let's just see what happens. So okay, that's a choice we're going to make. We're not going to use it yet. So now let's look at the next n that appears. These all have n equals 1. That one doesn't have an n equals 1, so I have to do n equals 1 separately. Okay, so when n equals 1, we get A1, 1 plus R, R, and A1, 1 plus R. This one doesn't have n equals 1, and this one is minus nu squared A1. That's the coefficient there. And this is all supposed to be 0, but the R is nu. So A1. And I'm going to assume that the A1 isn't, well, this isn't going to tell me what A1 is. I don't know. I have no idea yet. They all have an A1, so this isn't going to tell me what A1 is. A1 can be whatever I want. So I could choose it to be 0 if I wanted, but it's not going to tell me. So you've got A1. They've all got a nu in them. This one's got a 1 plus nu. This one's got... Oh, that one doesn't have a nu. Oh, bloody hell. So nu plus nu squared is 1 plus nu squared. That's right, nu plus nu squared. Yep, so that cancels with that. And we get A1, 1 plus 2 nu equals 0. Okay, so either A1 is 0 or nu is minus a half. So if nu isn't... Oh, but nu was... We were choosing nu to be positive anyway, weren't we? So, well, I don't know, it doesn't really matter. So... Yeah, because it was nu squared, nu was a positive number anyway, so nu can't be minus a half, so this is not 0, so A1 is 0 no matter what. That's so cool! Wow, okay. plus 2 nu is not 0. So therefore A1 is 0. Cool. That's nice. Okay, and then n is greater than or equal to 2, because now everything occurs in that. And so we can go back to our equations and pull everything out. Plus an plus r n minus 2 minus nu squared an. Okay, so we can lump all the ANs together. And that's minus AN minus 2. I guess the R is nu, so we've got n plus nu plus 1. What have we got there? Do not like it, Sem1. Oh, cool. Just factorise this, because they've both got an n plus mu, and then this cancels out, and so that's nice. So AN is cool. Okay. And so that's my recurrence relation, and you'll notice how this one, each one is based on the one that's 2 before it, and so the A0 will produce A2, A4, A6 and so on. The A1 will produce A3, A5 and whatever, but since the A1 is 0, all of the odd ones will be 0, and so I'm only going to have even ones. Just wanted to see how this worked so that I could follow how this process worked on something different. So, you know, A1 equals 0, so therefore A3 is like minus 0 over stuff, which is 0, and so on, A5, A7, etc. They'll all be 0. All right, A0 is whatever it is. And then A2 will be minus A0 over 2 plus nu squared minus nu squared, whatever that is. Cool. Oh, I can simplify that even further. Ooh. Just a second. N plus nu minus nu, n plus nu plus nu, because it's a difference of 2 squares. Ha. Fabulous. That's sweet. Okay. All right, and so on. So what they've done in the book when they did that is they have when they got to their Bessel functions have gotten to here. I'm not sure where the 2 squared came from. I might be doing something wrong in mine. Oh no, that's the initial equation that I got there. Oh, we said S equals 2m. What's S? S is our n? Yes, S is n. Ah, okay, cool. Okay. All right, so I'm just going to leave it there. I'll do one more. And so that's going to be whatever that is. And then each of them will be in terms of A0. And this way lies finding the Bessel functions. All right? So just to be sure, got A0 times x to the r, but r is new. X to the 2 plus nu plus blah, blah, blah. I'll only do the first two terms. Cool. All right, that's quite enough of Frobenius, I think, for me. I don't know how you feel. Yeah. So this is apparently j nu x. That's the name of this function. According, yeah, that's what it is. I just want to check if I've got things right here. So there's an x to the n is the nu there, so the next to the nu out there. And then it's only got the even powers, and they switch between plus and minus. That makes sense because of what was going on with the minus there. And then there's, well, other crap, but I can't be bothered making sure that matches. But most of the rest of it matches. It's got the negatives and the even powers, and so all of the rest of this must have come from dealing with this. Oh yeah, each one of them, it starts at 2 plus 2 nu, and the next one is another 2 above that, and the next one will be another 2 above that, and so I'll keep multiplying 2 plus 2 nu and 2 nu plus 2, and then 2 nu plus 4, and then 2 nu plus 6, and so that should be a whole lot of, that's like a factorial sort of thing, but it's going up instead of down, and so that's what all of this stuff here is about. Yeah, don't really get that bit. Yep.
Actually write out our final solutions for both the examples we just done. Do we need to have a summation sign in that as well?
Nah.
Can we just write it out as the A0 x to the power?
Just do the first few and then do a dot, dot, dot. That's what I would do, because I don't think you've been explicitly taught how to turn a recurrence relation into a formula for the single, to turn this thing, that recurrence relation, into this. It's not like you've been given methods to do that as far as I know. Could be wrong. Does that sound familiar to you? No. So you just do the first few. And in practical terms, the idea is that because you keep dividing by bigger and bigger things, the more terms you have, the less difference it's going to make to the answer. And so in practice, you'll just do the first several and go, well, it's approximately this. And you just choose how many terms you need to get the accuracy you want. So it seems like a lot of effort to go to if you're going to do it approximately anyway, but I don't know, mathematicians are nothing if not trying to find the most precise way of being approximate. Okay. Well, at least that's applied maths. Pure mathematicians are never approximate. They just study things that don't exist, so it's all good. Okay, so, all right, what am I going to talk about now? You call something out. Sorry? What was that? Okay. Do you have the... did you know exactly what that means? Waves in a pool doubles the Fourier series. This thing here? No. Modelling the vibrations in a membrane leads to the 2D wave equation this. Instead, here is a plausible argument apply Dirichlet boundary conditions to the A by B rectangle. The 3 steps invoke separation of variables twice. Oh, this has got 3 variables in it. Sure. Well, just based on what is written here, I have no idea what it means. There's a lot of details here that I'm not really sure going on. Most of your PDEs only have 2 variables involved, not 3. This one has 3. It has a t and an x and a y, and an outcome which is u, which is presumably the displacement above or below for the wave.
Are you sure just to show that, like, the derivative with respect to time?
So this is the past exam. Consider the problem of steady-state heat distribution in a rectangular region. The upper and lower edges of the region are insulated, while the left-hand edge is kept at a constant temperature 0, and the right-hand edge heated to some temperature distribution f of y. Sure, and why not? Write down the governing equation for the heat distribution in the region as well as the necessary boundary conditions. Use separation of variables to show that the entire family of solutions to the problem is given by that. Okay. Just checking. Hence, if the temperature distribution at the right-hand edge is that, find the set. Let's do it. I'm going to do it. So this is a PDE thing. So one thing that's different in this course compared to Engineering Maths 2A is that your lecturer, at least some of the lecturers in the past, have expected you to come up with a differential equation in the first place, based on the situation that's here. Whereas they don't expect that for the engineering students. But they only have 2/3 of their course as differential equations and the rest is statistics, and so they don't have time to, well, I don't know, maybe they're just more bloody minded in this course. So I just want to see if I can make sense of what's happening here. Okay. So, they haven't told us what function to use, so I'm going to let u be the u, x, y, be the temperature at point x, y. Okay. So I definitely know, just based on what this says, that u of 0y is 0, because the temperature is 0 in all of these positions. And I know that u of ay is whatever this f of y is. They feel like boundary conditions. And just with some colour coding, this one is because of this edge. And this one, no. This one is because of this edge. Okay. All right. I don't know what insulated means in this context. It must do something. Yep.
Derivative is 0.
That's what that means? Why?
Because it's insulated, the rate of change of heat is 0 because no heat is leaving the environment.
Ah, cool. Good to know. I'm just going to repeat that to see if I've got that right. So insulated means no heat leaving through that boundary. And so the rate of change of heat in the y direction as I cross that boundary is 0. So that would say that the rate of change of heat crossing that boundary is 0, and so that's saying that u y, that's the rate of change of heat in the y direction. Well, this says it's a steady state heat distribution. Is it the second derivative, the first derivative? Well, I'm just thinking, it says it's a steady state heat distribution, which means that it's not changing with time.
I think that's the big condition.
Sorry?
I think that's the upper boundary condition.
Oh, that's a separate condition? Whose solution is this?
Not so from the natural have outlook.
What is this d? Oh, is this a standard equation that goes with this situation? So I wish I'd known that. Like, I don't know any of these standard equations, because I've never studied differential equations myself. So you're telling me that there is a standard equation. Okay. That always goes with situations like this. So apparently what does this capital D stand for? Okay. For some constant D. Okay. Sure. So the rate of change of heat is some multiple of the sum of the two second derivative changes of heat, ignoring time. I have no idea why that would be true, and I can't give you any meaning on that, I'm sorry. But if this is the standard PDE that goes with how heat moves through space, that's the idea, then we know that at the steady state, it's not changing in time. Yep. And so we're going to get that that has to be 0. Because if this is 0, then either d is 0, which is stupid, or this is 0. Well, that makes sense to me that a steady state would mean that du on dt is 0. Okay, so apparently there's a standard PDE that does that. Okay, these are definitely true here. All good with that. That works for me. And then the insulated says, yeah, that's exactly what it's going to do. That the derivative in the y direction is 0 as you move across that boundary.
I haven't seen it in two-dimensional, but I've seen it in like one-dimensional.
Okay. Temperature does not change. And so therefore, that as I move across the boundary in the y direction, at the point where y is b, like that, no matter which x position I'm at, so just thinking about this boundary here, no matter which x position I'm at, if I move across that boundary, at no matter which x position I'm at the point where y is b, the derivative is 0. And you... Sorry? Oh, 0, duh, yes, you're right. That's 0 down there, isn't it? Like that. Okay. Right. Okay. All right, so I think I can now reconstruct the reason. We've reconstructed the reasoning that produces all of these things. We have a different, just to sum this up. To sum up, we have d squared u on dx squared plus d squared u on dy squared is 0. U 0y is 0. U a y is f of y. U y x b is 0. And u y x 0 is 0. That's what we have. Okay, cool. So I think, let me just go back to the computer. So I think this is so the difference between this wave equation and heat equation is the heat equation just has du on dt here, and the wave equation has d squared u on dt squared. Okay.
The equation for this question is the Laplace's equation in a steady state for equation 26.
Okay. In 2D space, steady in time, the wave PDE for membrane, the heat PDE for temperature field, or a PDE for soap film reduces to the elliptic Laplace's equation. Cool. Oh, okay, so those equations are quite different to begin with, but in steady state they all end up being the same equation. That's the idea? Okay. Cool. Oh, okay, so we've got these different people have different kinds of boundary conditions, apparently. Okay. So when it says Dirichlet boundary conditions, what are they? It specifies the value of u on the boundary. So in our case, we have a Dirichlet boundary condition on the left and right of ours. If I'm just making sense of these terminologies, a Dirichlet boundary condition here because it specifies the value of u, and these ones are Newman boundary conditions because it specifies the derivative on those boundaries. Okay. So I find terminologies pointless if there's no reason to distinguish between those things. But presumably they're important to distinguish because they produce different results when I attempt to solve them. So yeah, there's no reason to have squares and rectangles if you don't care about the difference between them. So okay, cool. All right. So apparently it looks like if in this course they'll give you situations that have standard PDEs to go with them, and you need to know what PDEs go with what situations. So you're going to have to know that. And I can't tell you that, but you can find it in your notes. You can find which ones go with what things. And presumably there will be... I hate telling people to do things by keywords. It is a bad idea. But presumably the situations will be about heat or changes in the heights or depths of things, which would be waves, or whatever the other thing was. There will be various situations that you can talk about. And I suppose heat doesn't necessarily have to be heat. It could be some other measurement. But yeah, okay. And waves don't necessarily need to be literal waves. They could just be changes in the value of anything, I guess. As long as they move in a wave-like way, it should be okay. Like the pressure in like if you've got living things all bouncing against each other, the concentration at a particular spot should do that too. Okay. Just making sure I've got an idea of what's going on here. I don't like keywords. You should never base it just on a word that's being used. You should always just make sure it seems to match the proper situation. Okay, so while we're here, we should know how to go about solving these differential equations, and that I can do. And as with all other methods that I know of in this course, it runs along the lines of assume your function is of a certain type, and then differentiate and sub it in and see what happens. Does your lecturer tend to use capital letters, the capital versions of the variables? Okay. Some lecturers use like F and G because they're the names of functions, so I just wanted to make sure. Sorry? Okay. Cool. At least I can remember which function goes with which variable this way. Okay. And so then the idea where x is a function of only x and y is a function of only y. Okay. So I'm going to need to know what du on d squared u on dx squared and d squared u on dy squared is, and so I can go so when I do this with respect to x, y counts as a constant, and so it will still be there multiplied on afterwards, and I'll differentiate with that. And when I do it twice, I'll get that. And d squared u on dy squared, the x will still be there, and I'll differentiate the y, and then I'll differentiate it again. Okay. And this is the crux upon this whole assumption of them being equal to this is going to make it work. Okay, and so we're going to have that x double dashed y, capital Y, plus x equals 0 when we sub it into the differential equation. I've just put all the x's on one side and all the y's on the other side. I'm just going to check something. Yep.
So normally there's like that constant p that is multiplying. Normally we keep that in there.
But it went away because everything was equal to 0.
Usually does the d teach you that kind of point just multiply the cost without the remaining sum.
So you were saying normally this d stays around?
That's if we have u and t as a continuous.
Yep.
Because it's 0, I think you can divide it out.
So I have a feeling there's going to be some situations in which you set up, like if it was a wavy, heaty thing, in which there's like a standing wave in the x or the y direction. And that's always the same in the x, but the y changes, in which case one of these is 0 and the d is still there. But what we had is that this one was 0, which means I can divide by the d. That's sort of what you were saying? That sometimes you can end up with that one being 0, in which case the d is still there. Okay. So, but what you're pointing out there, Jordan, is that there's often a number in this position here somewhere. And we're going to have to make a decision of where to put that number if it was there. I'll get to that in a minute. So, the key noticing that I'm aware of here is that this is a function that doesn't involve any y's, and this is a function that doesn't involve any x's, and they're the same function. So we have a function that involves no y's and no x's, which means it must be constant. And so we know that that this thing that is represented by both of these is a constant function. And so what we're going to do is we're going to attempt to figure out what that constant is. And the easiest way to figure out what that constant is to just focus on half of this equation at a time. So we need to, if we just had x double dashed over x equals 0, like equals constant, then that would be a second order d in one variable. And for a second order d in one variable, I would need to use my conditions for what happens in that variable to figure out what's going on in that equation. So this, if I did it with this one and that was a constant there, then I would go back to what was happening in my DE. And so if I knew what was happening when x... So this one, I would need to know what happened with at various values of specific values of x to be able to solve it. They would be my, I need to know that x is when x is 0 and when x is something else. And this one I would need to know what happens when when y was certain values. So when I know when x is a certain value, I get a function here, and that's not going to be very helpful because that's a function of y, and I'm specifically trying to avoid y coming into this formula when I have x. So that's not going to help. And so I really should be focusing on this one, which tells me what happens when y is a certain value, and the answers don't involve x. And so the x isn't going to come back into this equation anymore. And so, because the one where I choose various values of y give me plain numbers, I'm going to focus on this one first, which means I'm going to move the minus away from it. Or at least move the constant, whatever it is, away from here. So if it was like c squared, I would move it over here to be part of the x's so that the y bit is all by itself with no numbers attached to it. It's going to make my life easier. I think. Yeah. It'll work. Okay. So this is constant. Does your lecturer use K? Sorry? Yeah, I'll get there. Okay, so I will focus on this part first. Okay, so that is a second order differential equation with constant coefficients, and so I can use characteristic equation to solve that, and so like that. And so I will get lambda is plus or minus whatever the root of k is. So what the solutions are is going to be different depending on whether depending on the value of k. Because if k was negative, I'd get imaginary solutions and I'd use causes and sines. And if k was positive, I would get two real solutions and I'd get e to the power of stuff. And if k was 0, I would get a double solution, and they're all going to give me different things. And so I need to consider them separately. Okay. If I'm doing this properly, I need to do this whole thing. So, if k was 0, I'd have lambda squared equals 0, and I'd get lambda as a double root, in which case my y would be like y e. In which case my y would be like a e to the y plus b y e to the y, something like that. Only that won't be 0, just a second. Ignore that, ignore all of that. It would be a e to the 0y plus b y e to the 0y. That's how you do a double root. And so I will get a plus by. Okay. That's interesting. I need to just go back a bit and fix something. If we're going to focus on this, we also know... I'm going to need to insert a page here, I'm sorry. We know that... where is it? Must be here somewhere. We know that u of x is 0, which means we already have uy. That's x, y dashed, right? Okay. So uy is x times y dashed. We figured that out earlier. And so uy x b is x, x, y dashed b. And that's supposed to be 0 no matter what x is. And the only way that's going to happen is if y dash b is 0. And also uy of x 0 is 0, and so therefore we have x. And so therefore the y dashed has to be 0 as well. Okay, so just to sum up there, we now have y double dashed equals ky with y dashed of 0 equals 0 and y dashed of b equals 0. All right, that's the equation we're trying to solve. Cool. So now we focus on that equation, we do the characteristic equation and we get that. But we know that y dashed is just b. And so we know that y dashed of 0 is supposed to be 0, which means that b has to be 0. And in fact, this is telling us not the slightest bit of information about A at all. A can be whatever we want. Cool. Okay, so we have a solution there. one possible solution, just a constant. So if k was positive, then let k be like something squared. Yep. Yeah, y dash of b equals 0, which means b equals 0 again. Because y dash is b. Y dash doesn't involve a, sadly. But yes, I really should have covered it both. I was skipping that bit because I was looking ahead. Okay, so technically that means that since I don't really care about constants, one of my solutions is just 1. Okay. So let k be a positive number, so a positive, for... If it's... I'm going to have to square root it, so I might as well let it be something squared. So I've got two real solutions, and so my y is going to be something e to the mu y plus something e to the minus mu y. And y dashed is going to be mu a e to the mu y minus mu b e to the minus mu y, because I'll multiply by the mu. So y dashed of 0 is mu a e to the 0 minus mu b e to the 0, which is supposed to be 0, which means that a has to be equal to b. And y dashed of b, was it b? Yep. Is mu a e to the mu b minus mu b e to the minus mu b, which is supposed to be 0. Which means I get so since b is equal to a, I get that, and I get a mu times e to the mu b minus e to the minus mu b equals 0, and this number isn't 0, these two aren't the same number. E to the plus something can't be the same as e to the minus something unless they're both 1. And so therefore a has to be 0, which means b has to be 0, and we get y is just the 0 function. Now, did you want to ask me about anything or tell me something that's useful to know? Just wondering. If anything comes out, if anything came out of that conversation that would be useful for me to know.
You were saying that normally we don't have K0, like K0 having a solution. Most of the time when we have like K was 0 and K was positive, solutions are all trivial.
Yeah.
And so we just ignore them.
Yeah.
I'm saying that it's because it depends on the boundary conditions.
Yeah.
Certain times in the notes, we have specific times when given specific boundary conditions and specific problems, it tells us the answer, and I think we're allowed to jump straight to the answer in those circumstances. But if it's not something that we have memorized, like this specific example, we have to go through this entire process.
So yes, it's I'm going to repeat some of that. So in most of these stories, 2 of these come out to be just 0 and the other one isn't. But in this case, so far we've got one here and we're probably going to get some here too. And there are classic situations based on certain boundary conditions that will always produce the same kinds of answers. So I'm presuming that maybe that's the reason we have names like Dirichlet boundary conditions and Newman boundary conditions. So if they're all Dirichlet, then we can skip straight to an answer for this bit. That's sort of what you're saying?
Yeah, we can, like if we know the boundary condition gives the particular KW positive negative equals 0, we can skip that.
Okay. Yep.
So you
because we're steady.
If it's something like e keeps leaving it, you'll usually have an exponential decay term, so it will be the middle pair.
And so you'll end up with maybe this one's 0 but the b not, and go down negative. Okay, cool. Just going to finish it. I'm going to let it be something else. I don't like writing new, so the next available letter is rho. And so lambda squared is minus rho squared, so lambda is plus or minus rho I, and so my y is equal to a e to the 0 y. Well, I can just skip that. If you get purely imaginary, then you get purely like that. And so y dashed will be minus rho a sine rho y plus rho b cos rho y, and y dashed of 0 is, well, that would be 0 when y is 0, so we get rho b times 0, which is supposed to be times 1. So 0 plus rho b times 1, which is supposed to be 0, and so therefore the b has to be 0. Okay. So actually the y dashed is really the y's. So and y dashed of b, we already know that the b is 0, so that's just going to be minus rho a sine rho b, like that, because we know that the b is 0, so, and that's supposed to be 0 as well. Okay, and we know that rho isn't 0, and a, we really don't want a to be 0 because so far we've only got the solution of y as a constant. So if we're going to get any other solutions at all, we need the a to not be 0. So we're going to need sine of rho times b has to be 0, which means that b, rho b has to be an integer multiple of pi, because that's when sine is 0. If this had been a cos, it would have had to be an odd integer multiple of pi on 2 to make it 0. So we need rho b to be some multiple of pi. Now it's very important, I mean technically I'm allowed to use negative multiples of pi to get sine to be 0, but I know that neither b nor rho is negative. And so this has to be a positive multiple of pi. Because I assumed right from the outset that rho was positive so that I could do this calculation the way I wanted. Okay, so what does that mean? So to sum up, we've got so far, so just continuing my k negative situation, I've got that rho is n pi on b, which means the k is minus n pi on b squared, because k was minus rho squared. And it also means that the y is a cos n pi on b y. Because, just going back to here, the b was 0 and the a is, well, whatever a is. Okay. And so, to sum up, we have something along the lines of yn is going to be cos, which goes with k being minus n pi on b squared, and sort of y0 is just 1, which goes with k equals 0. They're the solutions we have. And we need to number them because there's a whole lot of different ones. And we don't need to worry about the a's, because we only want a solution, because later on we're going to multiply them by stuff and add them together anyway. So we can just worry about that. Okay, let's just see if that was the solution we were aiming for. That is not what I was expecting. Oh, no, it's not A. That's okay. It's all good. It's going to be fine. We're not even finished yet because we're only halfway. We're halfway. We managed to get to. So we've solved this half. Now we need to solve that half. So I'm just going to look at the lecturer's solution. Oh, he uses cosh and shine. Oh, that's fun. Okay. Basically, if you get two different real answers, like if you get plus or minus mu, then you can use cosh and shine as your things instead of e to the mu and e to the minus mu. Because cosh is. Sorry, you can just leave it as e. But cosh is e to the x plus e to the minus x over 2, and shine is e to the x minus e to the minus x over 2. So they're both built out of those two pieces. I know that cosh is the plus because cosh has the same answer as cos does when x is 0. And so it has to come out to 1. Okay. Sorry? Yeah. Okay.
So after you've got k is equal to negative pi over b squared, that be k n.
Yeah, sure. So when the lecturer did it, he did the cosh and shine and he ended up with trivial solution, and then did the cos and sine. Yep. Okay. So return to our earlier equation. Oh, and interestingly, we could actually call this cos of n pi on by for n being 0 if we wanted, because cos of 0 is 0. Cos of 0 is 1. So we could have actually just done it, included the n equals 0 in this one if we wanted. But I'm just going to leave it as it is for the moment. So let's return to the earlier equation, and now we're going to solve the other one. What's the other one? Here. Is that, which is actually this. So when the k0 is 0, when the k, we're going to have two different situations. When k is 0, we get minus x double dashed over x equals 0, and so x double dashed is 0, which means that well, I mean, if x double dashed is 0, we don't have to go through all of the characteristic polynomial thing at all. The second derivative is 0, it must be linear. Like that. Okay, and so we can find out what the a and the b are based on the conditions that go with x. The conditions that go with x are this one. So u0y is x of 0, y of y, which is 0, and so therefore x of 0 has to be 0, which means that a plus b times 0 has to be 0, which means that the a is 0. Okay, that's a good start. And u of ay is f of y, which means we have x a y of y equals f of y, which doesn't really help because y of y could just be chosen to be whatever f of y is divided by x of a. So that doesn't tell us anything useful. Okay, and so therefore the x is just bx for some b. Now since this went with k equals k0, we're going to go like that. Okay, and when k equals 1, 2, 3, etc., we get minus x double dashed over x is minus n pi on b squared, and so x double dashed equals x. And now when we use the characteristic equation, we get lambda squared equals n pi on b squared, and lambda equals plus or minus n pi on b. Oh, n, yep, gotcha. Yep. Okay, well, let's try this shine and cosh thing. That sounds fun. And so x is going to be something times cosh n pi on bx plus something times shine n pi on bx. Because that sounds fun to give that a go. And I'm not just doing it for fun. The lecturer said that there had to be a shine in the answer. And so I'm going to do it in terms of shine and cosh. So that's the alternative. Instead of using e to the power of, you can use shine and cosh instead, which are a little easier to differentiate.
I always like the derivative isn't the same, like they swap for the normal sign terms, they stay the same sign they've got.
Yep, so cosh and shine become each other for their derivatives and you don't get minuses happening.
Yeah, I always forget that.
Yep. Something to put on your... Okay, luckily I don't have to do the derivatives of these, so that's good. So my original thing is, so I know that u of 0 y is x of 0 y of y, which is supposed to be 0. So x of 0 is supposed to be 0. And so I get a times cosh of 0 plus b times shine of 0 is supposed to be 0. Shine of 0 is 0 and cosh of 0 is 1. So I get a equals 0. And so actually x is really just b shine n pi on bx. And I don't suspect we're going to get anything really useful out of the other bit either, because we're going to have that same problem of it coming out to a function of y. So this is the best we can get at the moment. U of a y, y of y is f of y. It's not going to be useful. Okay, so it looks like we're going to have xn is bn shine. So you may have noticed something that I did here that actually you wouldn't have noticed at all, that I always put a with the even functions and b with the odd functions, not just because they're in alphabetical order, but it does turn out to be useful in the end. So when I go a plus bx, a single plain number is even and x is odd as functions. And I put a with cos and b with sine, and a with cosh and b with shine. Yeah. So there you go. Okay. And so what have I got? Just to sum up. So when k is 0, I've got that the y was 1 and the x of 0 was b naught x, And so therefore u0 is x0, y0, which is b0 x times 1, which is just b0 x. And when n equals 1, 2, 3, etc., yn was, what was yn? Cos of n pi on by, and xn was bn sine n pi on bx, and so therefore un is the product of those things. I can tell that I am going to have real trouble remembering which part of it is the shine, has the H, which is the same as what the lecturer had, except they had A, whatever. I can change it to A. Okay. Yay! So, cool. What now? So just a second, let's just see where we've been. Created the equation, and then we suppose u was x, y, and we fiddled with the equation to get to the point where we had something involving x or something involving y is equals constant. We focused on whichever part of it involved equals constant in both of its boundary conditions. By boundary conditions with specific of y both produce a constant. In particular, both produce 0 would be useful. That's how I chose that. And then that allowed me to create this new set of differential equations. And then I had to figure out what happened for the different values of lambda, what the lambda squared could be. And we made a note back then that there are certain situations if all of the conditions are of a certain type, then you can just shortcut to the end, apparently. Some lecturers are very nice and will just helpfully tell you what the answer is if they don't want you to remember, but your lecturer seems to want you to know, so I would go having a look closer, and I reckon that might be the reason why we have Dirichlet and Newman and fixed and mixed. So if they're all Dirichlet, then you can run with certain things happening, definitely. Okay, and then we return to the other equation now knowing what... Yeah, probably. If they're all Dirichlet, I reckon you can probably skip to the end. So then we can return to the earlier equation. Now we know what k is, and it will tell us what these things are. And we get as much information as we can out of what we've got, and here we are. So the thing is that these are all different value, these are all different n possible solutions for what u is. And in fact, the real solution for what u is will be the sum of all of these things. Sweet. Sorry? Yeah. Fancy word is apparently superposition, which for mere mortals is add 'em up. Okay. So u is actually this. Sorry? Because this is different to that. This doesn't just have a plain x. So these ones, when n is greater than 0, I have this format with a cosh and a shine, and I have a different formula when u is 0, so I just put it as a separate bit.
Where that top one, did you get that from letting k equal different value?
Yep.
How can it be both?
So these are the ones that go with k, which is greater than 0, right?
Don't you have to choose one?
Nope. It's not, you don't choose. So this is what happens when k is 0. This is what happens when k is everything that's not 0. And we superimposed both of them. Superposed both of them. Yeah. Anything that you get from any of the values of k has to go together to make the final solution. Definitely.
It's like it's simple. We have like two solutions to the same thing.
Okay, so yeah, they correspond to
Basically. So yeah, we basically, technically we actually have x and this, and we've done b naught of, yeah, something like that. Okay. These are different homogeneous solutions, and we have to combine them all to get the full homogeneous solution. Okay, and then there is one piece of information that we have yet to be able to use, which was this thing with the UAY, and so we'll use that and see what we get. That's what we have. And this is supposed to be f of y, which is good because it is a function of just y, so that's useful. And in part C of this question, it says that this is actually 2 plus cos of 3 pi y on b. Which is a Fourier series already. I don't need to find the Fourier series of this, it's already a Fourier series. And so I will match up the coefficients. So this must be 2. So we have that the constant term, B naught A must be 2, in which case B naught must be 2 on A. And the coefficient of cos of n pi on by. Okay, so is mostly 0. Sorry, that's the constant. The coefficient of. Okay, so most of them are 0. Only one of them actually exists, and it's the one where n is 3. So 0 unless n equals 3. In which case we're going to get B3 shine of n pi A on B is 1. Sure, because n is 3. When n is 3, we get this, and so therefore B3 is 1 over shine of that. Are we allowed to use cosec? Why? No, that's just going too far. Okay. Yep.
Why is it like in Frobenius when we were solving when we did like sort of undetermined coefficients, and then if we were using our if we were putting in our initial conditions, we had to wait until we'd done the superposition before we use our initial conditions.
Mm-hmm.
But here it's like we can sort of do it at any time, and I'm not sure like.
Well, I think technically you're allowed to do it at any time if it helps.
Right.
Because one of them didn't help. This one didn't help.
So with the first one, you're allowed to do it before you find it.
I don't know. I think the idea is that the reason I was allowed to use this one is because that applied to all of the solutions simultaneously. I think if it gives the same result for every solution, then it's okay. I think you're right, because normally we don't use those until we get there. But this is all homogeneous anyway.
Okay.
I think.
Yeah.
Yeah. Yeah, I think the reason we can do it is because this equation to begin with is homogeneous. It didn't just have a floating function just sitting there. Like the equation that we had was equal to 0. And so we're allowed to apply the initial conditions because we don't need to add the particular solution at all because there isn't one. So that's why we can apply them as we go. Right. So if you're doing a homogeneous solution, you can apply the initial conditions when you want.
If there's a PDE, we don't use the method where we add a particular solution. We just, well, from what I've seen, we just assume that it separates and we go from it, even if it's not homogeneous.
Yeah.
And I would say that would we be able to do it as well?
Yeah, so because we're not using that same philosophy, we're not using adding particular solutions. I think if you look at all of them, then none of them are they're all homogeneous. There are no equals 2x. All right, we will have to compare just to see. And the best way to tell, and I'm making most of this up, is to compare them and say what is similar about these and what is different. So the thing that is different is what must be causing us to use a different method. So, yeah, but it is a different style of thing. I'm assuming that the solution is of a certain flavour rather than assuming that it's a homogeneous bit and then adding something on. I'm just going straight to the final solution. So maybe that's why we're allowed to do it. Okay, and so therefore, it's zeroness that all the other Bn are 0. And so my u actually, finally, I reckon I can fit it on the page. U of xy must be the B0 was 2 on A. And the only one of these that existed was when B was 3. And so we got 1 shine n pi on Bx. And then the constant that went with that was 1 on shine 3 pi A on B. Yep. Yay! A whole lot of things happened there. So if this function was not already written in terms of cos, I'd need to do a cosine Fourier series of it and match up all the coefficients, infinitely many of them. Yeah. And it has to be, I would have to do a cosine Fourier series of it because this is a cosine Fourier series. It's in terms of cos of stuff, because that's just a constant. Yeah. It does make me only mildly worried that there would sometimes need to be a shine Fourier series, but that's not something that you've talked about, and I've never heard of that, so I think we'll just here be dragons and ignore that bit for the moment. Okay. So one of the things that I've seen people try and do when they're studying for this is to look at this and attempt to find the Fourier series of this. You really need to notice that it's already a Fourier series. That's an important thing. And that was one thing that the exam writer in 2017 tried to do to make things easier for you. Yep?
Yeah, I feel like that's a likely condition as well, given how long it takes to get a Fourier series. Usually have to be stretched by parts in the exam. That's probably going to be too long.
Alternatively, you just write Bn equals this integral.
Yeah.
It's like, that's what it is. Because that's how you find the coefficients of a Fourier series with that integral. Yeah. Cool. Okay. So some useful things happened there, I think. Not just the general procedure, but a few little details along the way. Yeah. Well, it's probably time to stop since there's only a few minutes left on the recording. But we could make sure people get their bits and pieces back. I am interested in what this existence and uniqueness thing is about. I probably won't be able to deal with it, but I just want to see what it is. Is that this thing? This thing here? Consider the initial value problem. Consider the initial value problem y dashed equals f of xy. Okay, so that's a real classic one, you know, dy on dx equals some function of x and y, the sort of thing that you use Euler's method for. Back in Maths 1M. Okay. I think it was in Maths 1B as well, wasn't it? It's the one that where you, if you have an initial condition, you can use the fact that changes in y are approximately derivative times change in x. So if I knew that when x was x naught and then y was y naught, then I could figure out if I move the x by just a little bit, then the y would move by whatever y dashed was. And so I sub in here to get what y dashed is, and then that tells me how much y changes. And Euler's method just does that several steps.
Can that sound like Picard's iteration?
I don't know, probably. I've never heard of Picard's iteration. So, if in some rectangle the function is continuous and bounded, that's the definition of boundedness. Yep, bounded, and the size of f is less than k, then the IVP has at least one solution for x minus x naught in this zone. Further, also if fy, is continuous and bounded in the rectangle, then the IVP has a unique solution. Okay. It would be useful to have questions that tested the edges of that, like where the edges of that theorem are, like what it applies to and what it doesn't apply to. Sorry?
Y and x.
F of x equals y of x, or
One they used in one of the assignments.
So I just want to draw a picture of what this said. It said y dashed was f of xy and y of x naught was y naught. And this says that if there was a rectangle that contained x naught, y naught, it was like that. That's a rectangle of radius a in the x direction and radius y in the b direction. And as long as it's continuous, that this function f of xy is continuous and bounded in that zone, then there is at least one solution so in that zone the size of f is less than k, basically. That's what that's saying. Okay. then has at least one solution y of x minimum of a and b on k. Okay, so just a second. So there is a function of y as a function of x, and it works for x's that are in this zone. So just a second. So the options are, if b on k was less than a, then it would be like this zone here is where the function exists, that's the x-axis there. And if b on k is greater than a, then it's saying the function exists for all of this. Is that what it's saying? That's my x-axis there. I'm just redrawing this box here. Well, it has to be the less than whatever the minimum is. So I was just saying that if b on k is less than a, then it'll be less than b on k because that's the minimum. And if b on k is more than a, it'll be less than a because that's the minimum. Okay, so there is a function like in here somewhere that passes through the point I'm interested in that is definitely defined on this zone. That may be defined elsewhere, but at least it's defined on that zone. Okay, cool. And it's unique as long as the derivative with respect to y is bounded. But it's still on the same zone. Okay. So you're saying that one of the examples was y dashed is y on x, you're saying?
Oh, yeah, sorry. Yes, that was one of the
So that is, and you had something like that? Just as an example, I just want to see what I'm doing here. So this function is, as long as I can find a rectangle containing this spot where this is bounded, then as long as I can find a rectangle containing this point where that function is bounded, then there will be a solution.
yeah. I think if one was used as evidence of the region that is in a solution though, so it's like back.
Oh, okay.
They work backwards.
So that function isn't bounded if I go all the way past 0 for x, right? So the biggest rectangle I could fit around this would only be able to go this far, right?
Yeah. I think it was something like that. Yeah, you can't include the line.
I can't go across there, but I can make it as wide as I want this way. Okay. Okay, so in any of those, as long as this, so that's bounded in any of those rectangles, as long as it doesn't go all the way to there, it has to stop definitely before it gets there. And so therefore there will be a solution to this as long as, right, okay, cool. And so the solution will be but don't touch the y-axis, basically. Yep. Yeah. Well, not in rectangles that don't touch the y-axis, but in regions on the x-axis that don't touch the y-axis. Okay. So the widest interval that you could possibly achieve this function being defined on would be from 0 to 2. So we have